Hi, my name is Andrew Ferguson, and I'm going to introduce a concept we call participatory networking. This project is joint work with my colleagues at Brown University, Arjun Guha, Jordan Place, Rodrigo Fonseca, and Sriram Krishnamurthy. I'd like to start by talking about 4 problems we find in networks today. Something old in the home, something blue in the enterprise, something borrowed in the cloud, and something new in the data center. Recently, I was at home streaming a movie on Netflix. The playback was excellent. There were seemingly no bottlenecks between my laptop and the wider internet. But midway through the movie, disaster struck, and Netflix began buffering. The problem was a second laptop on the network had begun transferring files to my time capsule, which provides network-attached storage for automatic backups. This automated transfer over the local network caused my Netflix experience to suffer. After quitting the backup, Netflix's good performance returned. And this problem isn't unique. It can occur when streaming content inside the house, or when my laptop synchronizes with Dropbox while I'm watching YouTube or using Skype. In each of these cases, there's traffic on the network I care about as a user because I'm actively consuming it, and other traffic which is being transferred on my behalf, but which I don't care about the performance of. Well, today I can solve this problem by configuring special queues on my home router, or by implementing a protocol such as RSVP or even TCP/NICE. But despite all of these solutions to my problem, we still suffer these at home. And this problem can clearly be solved automatically. Applications such as Netflix, Skype, and YouTube know the bandwidth and latency requirements for a good user experience. And my OS knows which program I'm actively using. So why is this knowledge trapped inside the end host? The second problem I want to talk about is in an enterprise network. Here, there are multiple switches managed by dedicated network operators and numerous links which are shared by many users. In this environment, the heavy traffic on shared links can degrade performance for other users. So for example, if my server comes under a distributed denial of service attack, the first defense is to install a local firewall rule. However, if this is a UDP or TCP SYN flood, the packets will continue to traverse any shared links in the network. So my best solution is to contact the network operator and have the traffic dropped as it enters the network. But this solution is slow and fragile. It can take time for me to reach a human, and if the characteristics of the traffic change, then a new configuration must be applied. And this is not the only scenario in which a service wishes to use the network for access control. In recent work from Microsoft Research on the Azure cloud environment, a firewall is used to isolate untrusted customer virtual machines while booting. After boot up, the VM configuration can be made more secure, the firewall lowered, and the VM image transferred to the production side of the cloud. Well, they were lacking a practical API for managing the firewall via the VM boot service. So their implementation uses programmable MAC addresses on the servers, a static configuration on the firewall, and the usual duct tape we find inside networks to achieve their result. So again, we should ask, why is this knowledge about managing the network trapped inside the end host? The final problem I want to look at exists in current proposals for hybrid optical electrical networks. In these hybrid networks, connectivity is primarily provided by Ethernet running over the usual copper cables. But in addition, the top-of-rack switches are also connected by a fully optical network. The optical switch can create circuits between rack pairs, but cannot be reconfigured quickly because of physical delays while aligning the internal mirrors. In these current proposals, a management server monitors the traffic matrix on the copper Ethernet and uses a heuristic to detect large, long-lasting flows that would benefit from the higher bandwidth and lower latency of the all-optical paths. When such flows are detected, the optical switch is reconfigured, and the heavy traffic eventually moved to the new path. But this detect and react strategy is not always necessary. There are many applications inside the data center that know in advance how much traffic they will generate. For example, virtual machine migrations and the shuffle stages of MapReduce frameworks. So by now, I think you know the question I want to ask. Why is this knowledge about managing the network trapped inside the end host? So to resolve this question, we propose that regular users, applications, and end hosts be allowed to configure the network for themselves. We call this approach participatory networking. With it, end hosts, users, and applications inside of a single administrative domain inform the network control plane how to manage its many useful resources. This frees the network from the need to infer a correct configuration. In our prototype, users, their hosts, and their applications send 3 types of messages to a logically centralized controller, which we call pane. The first are requests for resources, such as guaranteed bandwidth, latency, path properties, or access control. And the second are hints about future traffic. And the third are queries for current or future properties of the network. The pane controller serves as an arbiter for conflicting proposals and ultimately performs the requested reconfigurations. While participatory networking provides a unified solution to the 4 problems I discussed earlier, this proposal raises a number of important questions which we've begun to answer. How can we do this safely? Can it be made secure? And will it be fair? And while we are still working to make participatory networking practical and eventually efficient, these are the same problems of resource management, protection, and isolation already solved in modern operating systems. Recent work to develop an operating system for the network as part of software-defined networking gives us the right platform to implement these features in the network. Software-defined networks provide support and abstractions for configuration programs to run on a logically centralized controller which can reconfigure the network. And like SDNs, regular operating systems began by providing resource abstractions to the applications and evolved into arbiters that support multiple principles controlling those resources. It's time we do the same for the network. Participatory networking introduces the end-user API, or the system calls, for software-defined networks. It does not propose any new mechanisms or network resources such as QoS, routing, or access control. It simply allows the end users and their applications to use them. Unmodified applications, or those which choose not to participate, continue to receive the best effort performance of existing networks. In our vision, the network operators will set baseline policies that enforce fairness and security, while end users and applications propose new configurations to meet their needs. The pane prototype has 3 main components. The first is the semantics of privilege delegation, the rules which reconcile new requests for the networks with the network's constraints. Second is the protocol, which allows the end users and their operators to participate. The third is the network controller, which implements the protocol according to our semantics. Today, I'll provide a brief introduction to the semantics, 2 short examples of the protocol, and also touch on the project's current status. Our paper contains additional details about pane and discusses the many previous efforts and prior works it builds upon. The first question we need to answer with pane semantics is how to divide authority over network resources. To divide authority, pane uses a hierarchy of network shares, which have 3 properties. Each share refers to a flow group, which is a set of traffic flows identified by standard attributes such as source and destination, IP and MAC addresses, protocols, and port numbers. Second, shares have a list of privileges indicating what can be performed using the share. For example, traffic can be allowed or denied, rate limited, waypointed through a particular switch, or provided with guaranteed bandwidth. Shares also authorize end users to issue hints or make queries about particular traffic. These actions can also come with restrictions. For example, bandwidth reservations are restricted using token bucket models. Finally, each share has a list of speakers or principals who are the end users authorized to use the share. A share's speakers also have the capability to delegate privileges by creating subshares. The creation of subshares is guided by the principle that you can't give away more authority than you have. For example, a subshare's flow group must be contained within the parent share's flow group. Here, our blue bar represents each flow group's range of source IP addresses. Furthermore, a subshare may not have a more permissive action set than the parent, and initially, the subshare's only speaker is its creator. Other users are later added as additional speakers. This process of creating subshares develops a privilege hierarchy we call the share tree. The root of the share tree is the root share, a share which contains all traffic in the network, comes with all privileges, and has a single root user as the speaker. The share tree only sets the static context for configuring the network. The actual configuration is performed by requests and hints to the pane controller. requests describe an action the speaker would like to perform on a flow group during a given time interval. After evaluating the request, the pain controller returns an immediate response indicating an accept or reject. Hints provide information about current or future traffic patterns. The pain controller is not required to respond to the hints and may optionally choose an action to perform on the traffic. Shares may also provide speakers with the right to issue queries about given flow groups, such as for traffic statistics. By design, a share's resources may be oversubscribed by its subshares. So for example, a share which is permitted up to 100 megabits per second of guaranteed bandwidth may permit each of its subshares to make reservations up to the same limit. In order to ensure that these restrictions are never violated, the new requests are recursively evaluated up the tree. So for example, if a user of share X requests 80 megabits per second of guaranteed bandwidth, the pain controller will accept the request and account for the reservation in share X and at the root share. Then if a user of share Y requests 50 megabits per second of guaranteed bandwidth, the pain controller rejects the request in order to prevent a violation at the root share. Finally, when accepted requests become active, the pain controller uses OpenFlow to reconfigure the network and implement the request. Now that we've explored pain semantics, we'll take a brief look at its protocol for interactively using and delegating network resources. As I described before, the privileges in pain derive from the root user's access to the share tree. To allow a regular user, Alice, to reserve bandwidth, root first creates a subshare with the appropriate flow group and privilege. In this example, the subshare is for all traffic sent or received by Alice with the authority to reserve up to 10 megabits per second of guaranteed bandwidth. After checking that root has the necessary authority to create this share, the pain controller accepts the request. But Alice is not yet a speaker on this share. As the root user is a speaker on this share, the root user can add Alice, and the pain controller will accept the command and add Alice as well. Alice now tries to make a bandwidth reservation using this share. She requests 5 megabits per second of guaranteed bandwidth for the next 10 minutes. Her message explicitly indicates which share she is using to make the request, and the pain controller will first check that the flow group on the request is a subset of the flow group on the specified share, and that Alice is an authorized speaker. As both of these checks are true, the pain controller next examines the schedule of accepted requests in the ABW share, and as there are currently no reservations, the controller now checks recursively for other reservations up the share tree. When the controller tries to install the reservation, it detects a conflict with the existing ones. Therefore, the controller denies Alice's initial request. Next, Alice retrieves the schedule of accepted requests from the controller and creates a new request for the same bandwidth, but now starting 20 minutes in the future. The controller takes the new request and checks if it can be installed at the new time. Because accepting this reservation would no longer exceed the limit, the controller returns a successful confirmation to Alice. When the reservation begins in 20 minutes, the pain controller will establish the appropriate queues on the switches and provide Alice's traffic with the requested bandwidth. Let's now consider a second example. If Alice wants to block some traffic to her computer, she can ask the root user to create a subshare for her with the deny privilege. After creating this share, the root user grants use of the share to Alice, as we saw before. Then, if Alice's computer is being attacked by Eve, she can send a deny request to the pain controller to have Alice's traffic blocked for the next 5 minutes. Because Alice was previously granted this authority, the pain controller accepts her request and uses OpenFlow to configure the switches and block traffic from Eve's computer destined to Alice. If Alice had tried to block Eve's traffic to another computer by changing the dest host parameter on her request, the request would be denied, as the flow would no longer be contained within the flow group that she had authority for. This has been a short sample of Pain's protocol. Our prototype supports several additional commands, for example, to establish rate limits, manage users, and query the state of our share tree. Since this paper was submitted, we've continued to develop Pain, and it now runs on a testbed network with multiple OpenFlow software switches. For the last 2 months, we've had several applications participate in the management of this network, and has been our own primary source of network connectivity. We've submitted a second paper that introduces new network abstractions we've developed and describes how we use them to implement pain and resolve overlapping requests within the system. This submission also contains experimental results showing the performance benefits to applications when they participate in network management. And I'd be more than happy to provide additional details about the current state after this talk. To conclude, I want to point out that today, 99% of the network configuration is written by less than 1% of the users. It's time to occupy the network. Now, participatory networking is not designed to overthrow network administrators. Indeed, it works with them. It introduces a management API with syntax and semantics for delegating authority from the operators to the end users, and provides a network controller which implements the API by processing commands and resolving conflicts. Participatory networking makes joint management of the network safe by only allowing actions which are explicitly permitted, secure by checking messages at a single logical controller, and fair by accounting for resources and granting requests according to the user-specified policies. I'm happy to take your questions at this time, or you can direct them to my collaborators in the audience. Thank you very much. Yeah.
Now we have the tools in place, but rather than the user having to go ahead and do some provisioning, you could have some network behavior analysis tool or something that run in the background and use this framework.
Exactly. That's exactly our vision. We'd like Netflix to be able to talk with the network control plane about its desires and have that taken care of automatically. Yes?
So you talked about bandwidth reservations and using OpenFlow. How are you doing that? Because the current OpenFlow specification doesn't provide for that.
So the OpenFlow 1.0 extensions provide for enabling queues in band with OpenFlow, and you can use out-of-band commands with Open vSwitch, and those are the two mechanisms that we use at the moment.
Okay.
Any further questions at the moment? Okay.